Algebra 2, Chapter 10, Section 1, Exponential Functions. Many quantities change over time by a constant factor. For instance, if you have a bank account balance that doubles every 10 years, its value is increasing by a constant factor. When you hear factor, you should think multiply. Okay, so if you have a bank balance B and it doubles every 10 years, then you would have whatever the balance started as, it's doubling every 10 years, so it's exponential. So after 10 years, so my bank balance after 10 years would be twice my bank balance that you start with, and my bank balance after 20 years would be double the bank balance at 10 years, or 4 times the original bank balance. And at 30 years, we would have double this, which would be 8 times the initial bank balance, and so on. So we can see we're growing by constant factor, not a constant rate. Constant rate is linear growth. A constant factor is exponential growth. Exponential. So we can express an exponential function of t in the following form: a times b to the t, where a and b are constants and b is bigger than 0. So notice here that our input to our function is in the exponent, not the base. This is a new concept for us. And this is the core of an exponential function is a constant to a variable power. We call a the initial value because that's the amount the quantity starts at, and b the growth factor, and often we even write a as q naught, which means initial quantity. But we'll keep b for growth factor. Natural domain of any exponential function is the set of all the real numbers, so we can put any real number in as the exponent. But the range that we get out will be a positive number, because even its negative power gives us a positive number, right? If we take 2 to the negative 2, we get 1 over 2 squared, which is 1/4. So the more negative we get in our exponent, we stay positive, but we get smaller and smaller. Now if a is negative, of course, it inverts that whole thing, and we would have a negative range. All the negative real numbers would be our range. So let's do an example. Are the following functions exponential? If so, identify the initial value and growth factor. So part A, the answer is yes. And the initial value is 275. And the base, the factor, is 3. How do I know it's exponential? Because it fits the form. We have a, a, b, to the t. B is yes, a is 80, b is 1.05. And c, the answer is no, because the variable is in the base, not the exponent. The variable is not in the exponent. In fact, it's a power function, because we have a variable to an integer power. Let's model each situation with an exponential function. A, the number of animals in a population is initially 880, and the size of the population increases by a factor of 1.14 each year. So here we have the number, and t is in years. B, the price P of an item is initially $55, and it increases by a factor of 1.031 each year. Again, t is in years. After being treated with bleach, a population of bacteria begins to decrease. The number of bacteria remaining after t minutes is given by the following exponential function. G of t is 800 to the 800 times the 3/4 to the t power. Okay, so a is 800 and b is 3/4. Find the number of bacteria at 1, 0, 1, and 2 minutes. So at 0 minutes, we have 800 3/4 to the 0. And remember, any number to the 0 power is just 1. 800 times 1 is just 800. So after 0 minutes, we have 800. At 1 minute, we have 800 times 3/4. So 3/4 of 800 will be 600. Because 800 divided by 4 is 200, times 3 is 600. And what about at 2 minutes? Now we can find 800 times 3/4 squared. We could also think of this as just the previous result times another 3/4, sort of incrementally. Okay, and here you'd have 150 as 600 over 4 times 3 is 450. You can see that here we lost 200 bacteria. This is probably millions or billions of bacteria, but whatever the units are, we weren't told us. Here we lose 150. So each minute we're losing fewer bacteria due to the exponential nature of the decay here. So we call this decay because b is less than 1. The quantity is decreasing. We're multiplying by a number smaller than 1. If b is bigger than 1, we call it growth. Okay. And of course, if b equals 1 exactly, then it's a constant. We'd have 1 to the t. It doesn't matter what we raise 1 to, we stay with 1. Which is a weird case. We could write it here. If b is 1, we have a constant, which is not even really exponential. It's just a degenerate case. Which of the following functions are exponential? If so, again, identify a and b. Now we have to do a little work to see if they are. So let's first do some work here. We have 2 to the negative t and 3. So let's split this fraction up to 1/3 times 2 to the negative t. Now we can remember that a negative exponent means that we can flip the inside by factoring the negative 1 out and using our rules of exponents. So here we have something that looks like an a and b to the t. So a, the answer is yes, it's exponential. A is 1/3, b is 1/2. And that's the answer to a. B, we have the square root of 5 times 4 to the t. Using our rules of exponents, we can break this. We can think of this as to the 1/2. We can then, we have used the rule about common exponents to get 5, where we take the exponent of each, 5 to the 1/2 times, and then we use the common power rule where you multiply the exponents. For 1/2 times t is t over 2. Now we're not quite to where we need to be. 5 to the 1/2 is the square root of 5 is a number, but here we have 4 to not just t, but we can fix this by breaking this back into 4 to the 1/2 to the t using the rule where we can swap the order when we multiply the exponent to the exponent rule. And now we have a number a and a number b, which we can also write. We generally write these numbers like this. The square root of 5 is the square root of 4. And of course the square root of 4 we usually just write as 2. So now we have, yes, a is the square root of 5, b is 2. C. Well, here the variable is not in the exponent. The variable isn't the base. So this is another power function. So the answer to C is no. It's not exponential. It's not exponential because t is not, the variable is not in the exponent. And let's also talk about for a minute here what shape the graph of an exponential function has. So let's draw some axes and label them. So this will be our input. Maybe it's time. Here's our quantity. It's a function of time. Remember, our quantity is going to be a times b to the t. Okay, so let's just graph a few here where let's start with b is 1. So if b is 1, remember that's the degenerate case where we have, let's put 1 here. Whoa, that looks funny. Let's try to make our tick mark a little bit better. So we have 1 here. And let's put on the input side here, let's let it spread it out a little bit. 1, 2, 3, negative 1. And I'm doing this to show the shape of the graph. Negative 2 and negative 3 over here. We kind of went off our axis. So let's fix that. We'll just draw it over here. We'll pretend that's a straight line. Maybe it'll be better to just freehand the extension. So I can't line my rulers up very easily. So now we have a nice little graphing setup. So if we were to graph where A and B are both 1, then we would have a straight line. Just make this straight line light blue. We'd have a straight line that goes through 1. It's parallel to T. And this is when A is 1, B is 1. Remember, that's a degenerate case. So we just have 1 times 1 and T. That doesn't matter what T is, we end up with 1. But we'll draw that here as a reference. So now let's use red and think about, what if B is 2? So if B is 2, when we have 0 as our input, we will have, we'll write this down here. So if B is 2, and we'll just do, A is going to be 1 for all of our, maybe we'll do some with a negative. So A is 1, B is 2. That gives us 1 times 2 to the T. Okay? So 1 times 2 to the T is just 2 to the T. So 2 to the 0 is 1. 2 to the first power is 2. 2, 3, 4, 5. Let's go ahead and 6. Draw some more tick marks on our axis here. So when the input's 1, we get a value of 2. When the input's 2, we have 2 squared is 4. And when the input is 3, we have 2 cubed is 8. Okay, we can join these up with a curve. And as you can see, it gets steeper and steeper as the input goes up. That's the nature of exponential growth. Now, if we think about negative exponents, t to the negative 1 would be 1/2, because we would have the inverse of 2, and t to the negative 2 would be 1/4, and t to the negative 3 would be 1/8. And now this side will approach the axis, but will never actually really touch it. It's just going to be very close to the axis, which makes it hard to kind of freehand a graph here that's very accurate, but hopefully you get the idea as we connect the dots. So this is when B is 2 and A is 1. Now the bigger we make B, the steeper this exponential growth will be. If it was 4, we'd have 1, 4, 16. We would quickly go up. And if B is smaller, but still greater than 1, it'll grow less steeply. And it will shrink less steeply this way. Okay? Now what happens if A is negative? If A is negative, we would have just the opposite of this. It would be flipped around the t-axis. So if we have 1, 2, 3, 4, 5, 6, 7, 8, you'd have negative 1, negative 2, negative 4, and negative 8. And on this side we'd have negative 1/2, negative 1/4, negative 1/3, negative, 1/8. So you see it's just the same shape reflected about the t-axis, the input axis, when we negate A. So this is A is -1, B is 2. And if we have a number that's less than 1 for our exponent, suppose that we want to try 1/2, then we would have 1/2 to the first power is 1/2. 1/2 squared is 1/4, and 1/2 cubed is 1/8. So you end up with the decay. It's going closer and closer to the t-axis, but never touching it. So it looks kind of like it's touching it here. It's just me not drawing it very well. It doesn't ever actually touch the axis. Let's try drawing it again without touching it. Okay. And it just keeps getting closer and closer without ever touching. -1, now if it was 1/2 was b, if b is 1/2, then -1 we would have 2, -2 we would have 4, and -3 we'd have 2 cubed is 8. So you can see in the negative input side we have this steeper decay down to 1. And this, when a is 1 and b is 1/2, you can see that the graph really reflected around to the output axis. And of course we can apply what we know of shifting and scaling to move graphs, exponential graphs around by altering the input and the output as well. And we'll talk more about that in the upcoming sections.